Okay, hey guys. Today we're going to talk about rational functions. Okay, rational functions are basically just another word for fractions. Rational is another word for fractions. And so we're looking at what those graphs look like, what kind of properties that those graphs have. The first property we want to talk about is holes. Graphs can have holes. They can just be going along and have a hole in the graph. How do you know when you have a hole? It is when you want to cancel something out after you've factored it, and it's what makes that part 0. For example, if I have y equals x minus 1 over x plus 3 times x minus 1, we have a denominator that has already been factored, but when you look at it, you want to cancel out this x minus 1 and this x minus 1. We're used to doing that. When that happens, when you have that desire, you have a hole in the graph, and the hole is occurring where that would be 0. So we would have a hole in this graph at x equals 1, because if I plugged 1 into that part, it would be 0. Now, what's left, if I just looked at that, y equals 1 over x plus 3, that is the shape of the graph. So the graph is shaped like your toolbox function 1 over x, move left 3, but you're going to have a hole at 0. Okay, the next thing I want to talk about is vertical asymptotes. Vertical asymptotes we have seen before in this class. We've talked about them with the tangent graph, and we talked about them with our toolbox functions 1 over x and 1 over x squared. As you know, vertical asymptotes are lines that the graph gets close to, but it doesn't cross. How do you know when you have one? Well, that's what I'm talking about right here. If you look at the equation, you're looking for what would give you a 0 on the bottom that isn't already a hole, and sometimes you don't have holes. This example that I have chosen here doesn't have holes because you don't want to cancel anything out. So if we're looking for vertical asymptotes, all we have to do is look at the bottom and see what would give us a 0. So if I plugged a 3 in here, or a negative 4 in here, I would get a 0 on the bottom. So my vertical asymptotes are x equals 3 and x equals negative 4. Now, those are important to have the x equals with them because they are lines. They are equations of lines, and as you know, the equation of a vertical line is x equals a number. Okay, the next thing that we want to be able to find when we're looking at a rational function is where are zeros, where are its x-intercepts, where is it crossing the x-axis. So the way that we do that is similar to what we did for vertical asymptotes. We are looking for what gives us a 0 on the top. But again, if it's a hole, you don't include it, because obviously if it's a hole, it can't be crossing at that point. There's nothing there. So when we look at this example, the first thing I do is look for holes. And again, I want to cancel out these x plus 2's. So that means I have a hole in my graph at negative 2, because that would be where that would be 0. And since I'm looking for zeros and x-intercepts, I'm going to look at what's left on top and decide where that would be 0. Well, if I plugged a 1 in, I would get a 0. So my 0 for this function is at x equals 1. Sometimes you have zeros, sometimes you don't. It just depends on whether the graph crosses the x-axis or not, and it doesn't have to. In this case, it did at 1. Again, if you wanted to look back, your vertical asymptote here would be at a positive 4. So if you wanted to make that note, vertical asymptote would be at x equals 4, because that would be what gives us a 0 on the bottom. Okay, the last thing that we're going to look at are horizontal asymptotes. So these are horizontal lines that the graph gets close to. We determine that by looking at the highest power of x on the top and the bottom. And obviously I have the most simple situations here, and we would normally reduce something like this, but I'm wanting you to imagine that there's other things added out here or multiplied out here, and we're just focusing on the highest power of x. If you're in a situation where it's small over big, like x over x to the fifth, this is a smaller power than this one, the horizontal asymptote will be at 0. So you would write y equals 0 for your horizontal asymptote, because this is how you write the equation of a line. If it is a big over small, where the biggest is on top and the smallest is on the bottom, then that graph actually goes off to infinity. Well, if it goes off to infinity, it doesn't have a horizontal asymptote, so you would write none. And then if you have the same power of x on top and bottom, you do coefficient over coefficient. In other words, you're going to focus on these front numbers here, and your answer comes from those. Because you have x to the fifth on top and on the bottom, you use the numbers in front of them. And so, didn't mean to write equals there. Your horizontal asymptote would be y equals 2/3. These three situations I wrote up here because you're going to use these same rules when we get to limits later on, and I just wanted you to be thinking like that already. Okay, now we're going to do some examples where we find everything that we possibly can. In our first example, you want to look at it and see if you can factor. This one does not factor. Nothing happens on top, nothing happens on the bottom that we can work with, so we're just going to look at it like this. Wholes. Do you have anything that you want to cancel out? Well, nothing is perfectly matching, so no, you can't cancel anything out. Some of you might say, I want to cancel those x's out, and that's a common thing for people to want to do, but when this is attached to this 1 with this plus, you can't cancel like that. You can only cancel up and down when you're multiplying. Addition and subtraction mess that up for you. So since nothing cancels out, we have no wholes. And you need to write none or something like that so that I know you realize there are no wholes. Don't just leave it blank. The zeros I'm going to do next because that's the next easiest. The zeros is when we're looking at the top and deciding what the 0 would be on top. What would give us a 0? And obviously it's 0. So my 0 is at x equals 0. We're crossing the x-axis at 0. And again, I'm skipping over vertical asymptotes. I'll come back to it. Horizontal asymptote, I want to look at the powers of x. I have small over big because x to the first is smaller than x squared. Small over big is 0. So my horizontal asymptote is at y equals 0. The last thing I'm saving is the vertical asymptotes because that's where you look at the bottom and decide what would give you 0 on the bottom. And in this case, it's kind of hard to think about. You might try some different stuff in there. If you plug in something like 1, you're going to get a positive number on the bottom. If you plug in a negative 1 and square it, you're going to get a positive number on the bottom. In fact, anything you plug in and square becomes positive, and so you're getting a positive number plus a positive number, and you're like, what is it going to be? If you're not sure what would make the bottom 0, do an equation. Come over to the side and do some scratch work. Set it equal to 0 and solve. Here I would subtract 1, divide by 3, and then take the square root. As we learned recently, this would give us an I. And so an I is not an actual location where we can draw a vertical asymptote. So there are no vertical asymptotes on this graph. You don't always have to have them. Okay, for our second example, I'm using this one. 2x squared over x squared minus 1. And before I factor it, I want to do my horizontal asymptote because it's easier to do your horizontal asymptote before you factor. I have x squared on top and x squared on the bottom, so I have the same over same. So I look at their coefficients. Here I have a 2, here an imaginary 1. So 2 over 1 gives me a horizontal asymptote of y equals 2. Before I do the other stuff, I want to factor. The top doesn't factor. The bottom is a difference of perfect squares. I'm not sure why I wrote 2. I was thinking about that 2 on top. So x minus 1 and x plus 1. Okay, holes. Does anything cancel out? And obviously nothing does, so again I have no holes. Then I ask myself for vertical asymptotes, what would give me 0 on the bottom? 1 or negative 1. So my vertical asymptotes are x equals 1 and x equals negative 1. Zeros are where the top would be 0. So again, 0. That's what would give me a 0 on the top. So that's how I'm going to look at this problem. For our third example, we're going to do this function here, and I'm going to look at it first to see what my horizontal asymptote would be. And when I look at the powers on top and the powers on bottom, the highest power is x squared. So I have x squared over x squared. My coefficients are understood ones, so 1 over 1 is 1. So my horizontal asymptote is y equals 1. To figure out the other stuff, I need to factor. So this is x factor factoring. On top I get x plus 2 and x minus 1. On the bottom I get x plus 2 and x minus 3. So I want to see, do I cancel anything out? Yes, I want to cancel out these x plus 2's. So that gives me a hole at negative 2's. What makes that 0? Then I look, what would give me a 0 on the bottom of what's left? Positive 3. So vertical asymptote at 3. Then for the zeros, I look at the top. What gives me a 0 on top? Positive 1. So everything was represented in this problem. And for our last example, number 4, we have this really complicated looking function. And I've chosen this one because it is a little more complicated than the rest. If you are first looking at the horizontal asymptotes, you have the same power of x on top and bottom. Both are x cubed as your highest power. So you look at your coefficients, 3 and negative 4, and you make your horizontal asymptote y equals negative 3/4. Then you're like, okay, I need to factor. Well, this doesn't factor. Although it is a trinomial, it's not a quadratic, so we can't use the x factor or use the quadratic formula to help us to factor it anyway. So you're kind of stuck. Well, at that point, you can decide, well, nothing's going to cancel out, so I have no holes. Then we get to those questions where you have to figure out what you could plug in and get 0. On the bottom, for the vertical asymptotes, it's one of those times where it's not really clear. So come and do some scratch work. You have negative 4x cubed plus 5. Set that equal to 0. I'm going to add the 4x cubed, divide by 4, and then take the cube root. So that tells me what would give me a 0 if I plugged it in, and therefore that is my vertical asymptote. X equals the cube root of 5/4. Now, for the top, where is the top 0? You can ask that same question. 3x cubed plus 7x squared plus 2. But again, it's not factorable, and you can't use something like the quadratic formula because it's not quadratic. So this leaves you with one question, or one option, and that is to graph it using your calculator, which I cannot show on here because I can't put my calculator on this screen. So trust me when I say that we graph it and find a 0 at negative 2.44. I would recommend you pause the video and graph it and make sure that you can find that 0. Okay, the last thing that I want to mention is about domain. Your domain is going to be everywhere but your holes and your vertical asymptotes. Because your holes and your vertical asymptotes aren't actually points on the graph, so your domain will have every x value but those. So for example, if I had y equals 1 over x minus 3 and x plus 2, I would have vertical asymptotes at 3 and -2. So my domain would be all real numbers not equal to 3 and -2. The video is done. You can rewind if you need to. If you are ready for the assignment, come see me.